we are now going to use the HEC-RAS program to hydraulically analyze a subcritical transition. The assumptions that we will make: it has a steady state flow rate, and both up and downstream from the transition would be long prismatic channels, and we will assume a constant channel roughness through the transition. The definition of variables are those which we normally use in the course. So every variable on this list we have used repeatedly to represent an open channel parameter. For this particular example, we're going to take a trapezoidal channel, then we're going to go through a wedge transition and end up in a rectangular channel. The trapezoidal channel has a bottom slope of 0.002, a roughness of 0.02, a bottom width of 10 feet, side slope of 2 to 1, and it's going to carry a flow rate of 400 cubic feet per second. The loss coefficient for the wedge transition will be 0.2. Finally, getting into the rectangular channel, it will steepen up a little bit and have a bottom slope of 0.004. It will have a comparable roughness of 0.02, a bottom width of 12 feet, and carry the same flow rate. So we need to know the properties of the wedge transition in order to link the trapezoidal and rectangular channels. First, we would begin by getting the normal depth of the trapezoidal channel and the critical depth. So you can see that the trapezoidal channel, because the normal depth is larger than the critical depth, it's a mild channel. We would then get the normal depth and the critical depth for the rectangular channel. Once again, the normal depth is greater than the critical depth, so we do have a mild channel. Looking at the property of the wedge transition, we will start by simply linking the wedge transition to the two channels by averaging the bottom slope. If we average the 0.002 and the 0.004, we would get a bottom slope of 0.003. In the design of subcritical transitions, the convergence angle has been found effectively to be 12.5 degrees. So now, after we have calculated the normal depths, we can see at the downstream end the normal depth would exist of 3.97 feet at the outlet of the wedge transition. On the upstream side of the wedge transition, we don't know yet what the depth will be because we will calculate that moving through the transition. If we look at the plan view of the transition, showing only the water surface, this is what's going to be contracting from a top width of 28 feet to a top width of 12 feet. So the transition length is based on the contraction of the water surface. So the transition length would be 0.5 times 28 minus 12 divided by the convergence angle of 12.5 degrees, taking the tangent. That would give you a length of the subcritical transition of 40 feet. Actually, you'll notice it would give it to you at 36 feet, and then you would more than likely just round up to 40. Now, if we look at the plan view of the constructed transition, Section 5 and Section 4 would be in the trapezoidal channel. Section 2 and Section 1 would be in the rectangular channel. Notice the numbering is according to HEC-RAS, going from downstream to upstream. We will add Section 3 which would be right in the middle of the channel transition. If we look at the cross sections, sections 4 and 5 are in the trapezoid and have a 10-foot bottom width and a 2.5 to 1 side slope. Sections 1 and 2 are in the rectangular channel and have a 12-foot bottom width and also a 5-foot height. If we look at section 3 for a wedge transition, what happens in the wedge is that the side slopes of the trapezoid continue until they intersect the walls of the rectangular channel. So you can see this particular cross section is a combination of the trapezoid coming in to join the rectangle. So the trapezoidal part would go up 2.5 feet, and then the rectangular would go up 2.5 feet. The bottom width would be 11 feet, which would be halfway between the 10 and the 12 feet from the adjoining channels. Now we're going into HEC-RAS. So at section 1, I've given the 4 points describing the station and the elevation at the downstream end. I've done the same thing for section 2. And if we go up to section 3, that would be the combination of the rectangular and the trapezoid in the wedge part of the transition. Then you see for section 4 and section 5, I have also provided the coordinates for the trapezoidal channel. So open the HEC-RAS program. Enter the cross-section data into the HEC-RAS program and determine the water surface elevation for 2 cases. The downstream boundary condition is at the normal depth, and then take the downstream boundary condition 1 foot above the normal depth, assuming that some sort of backwater condition exists. Fill in this sheet after you complete your HEC-RAS simulations so you can compare to the answers on the next sheet. This sheet is available in HS-020, also for printing as a handout. Here are the answers that I obtained when I ran the simulation. And now you'll notice that the 1 foot difference is almost entirely gone by the time you get up to section 5. It's even almost entirely gone as you get to section 3. So you notice the 104.97 would represent an M1 curve starting at the downstream conditions. And for this particular channel, the M1 curve quickly almost returns to the normal depth.